throughout the state, and just show our vision and our mission statement there as part of FORS to support the recovery of Florida's oyster habitat and fisheries with science and through collaboration. So let me see, what's our next? There we go. So we work with professionals throughout the state of Florida, and this is kind of what we're trying to do here with FORS. Foster the comparability of science-based metrics, methods, and models, develop science-based guidance, support status and trend assessments that are actively being done through the Oyster Integrated Mapping and Monitoring Program and CCAR, and eliminate barriers to oyster restoration recovery. And then in turn, share that information with the broader oyster community. So I'm going to leave this up here for just a minute or so while I'm admitting everybody in. This is our web page. If you can scan that QR code, that'll get you to our web page, and it's also there's a link in there to join our listserv so that you'll find out about these webinars in advance, and also to kind of look at what FORS has been doing so far. There's links to the guidance documents that we've developed, and also a link to our YouTube channel that has archived a lot of these webinars. So there's actually, it goes back quite a bit. And so I just want to also remind you that our next one is September 17th. Dr. Juan Esquivel Milbert, I think is how to pronounce that, from Macquarie University in Australia, is going to be our next presenter in September. You can scan that QR code to register. I will post paste that link, that Zoom link, in the chat as the presentation is ongoing. And right now, I'd like to introduce our guest speaker for today. That's Dr. Gregory Herbert from the University of South Florida, and talking about the relevance of historical data relevance of historical data for managing West Florida's oyster habitats in a changing world. Dr. Herbert investigates the ecology and evolution of marine ecosystems with a focus on shelled marine invertebrates. And uses a lot of different tools to determine the extent of human impacts on biodiversity and providing actionable information on conservation priorities to policymakers. So we saw Dr. Herbert's shorter version of a presentation at the Oyster Integrated Mapping and Monitoring Program, and we thought this would be a great opportunity to kind of have him present an expanded version of that shorter presentation. So we're really excited for him to come here and share his research with you. Dr. Herbert, again, he got his PhD from UC Davis and has been with USF, University of South Florida, since 2005. And I originally got a start in Louisiana at Loyola University. Is that correct, Greg?
It is.
As your bachelor's, yes, great. So with that, we'd like to welcome Dr. Herbert, and I will stop sharing, Greg, and allow you to share your presentation.
All right. Can you see that, Vincent?
Yes.
Okay, great.
It's great.
Okay. All right. Hi, everybody. I'm Greg Herbert from University of South Florida. Vincent gave a quick intro, but I'll just tell you that I got my PhD in geology, but I was also in the Pop Bio grad program there. So I have broad expertise in geochemistry, paleo, and marine ecology. I started off my career at USF working more on paleobiology, but I've drifted more and more into conservation, restoration issues. Today, my talk's going to focus mostly on how oyster reefs functioned in the past in Florida and how they function versus how they function now. And along the way, I'm going to try to address some of the FOR's goals, like status and trends assessment, barriers to oyster management, and the consensus on metrics and modeling parameters. All right. So one of the things that we know is that oyster reefs, they collapse. They don't fade. And we've seen that in quite a few places. Suwannee Reef is one of the best examples of this. In the last few decades, there's been a decline of 88% of the offshore reefs. And once those offshore reefs were weakened, that really it decreased the ability of these estuaries to impound fresh water, and that led to invasions of uh, disease, parasites, and predators, and that caused further loss of inshore reefs and movement of reefs upshore. The Apalachicola reef fishery is another big example of how oyster reefs don't fade, they collapse. This is the OIMP data, fisheries landings data, and you can see that there's a couple of points where there was a hurricane and a drought that influenced landings, but in last couple of decades, the collapse was pretty severe. And one of the things that has taken people's attention is that once these reefs collapse, they have a hard time coming back. They really resist restoration. Bill Pine wrote a paper about this, just trying to figure out what on earth is causing restoration to be so difficult once these reefs disappear. And his critique was that the hypothesis that we're testing is often limited to substrate. Are we using the best kind, the best amounts? An alternative hypothesis is that these reefs are operating already in a collapsed state, and it just takes a little bit to knock them over. And once they're knocked over, it's very difficult to get them back. And before I go any further, I want to make sure I acknowledge that a lot of the research that I'm going to be talking about is really based on work that Eric Powell and Roger Mann have done on the Atlantic coast. It really hasn't been brought down and applied to Florida, but I think it does. It works here too. All right, so the basic problem I think with oyster reefs in Florida has to do with shell budgets. We know that the shell production on the surface of a reef, it needs to approximately balance the shell loss below in order for the reef to maintain the functions that it does. So the dead shell that's below, that's actually the oyster population's life support system. It provides a substrate, as we all know, for oyster recruitment. It baffles destructive wave energy during storms. It forms dams that impound fresh water, and that's really important for getting rid of enemies like parasites and predators. And then also because the bottom waters can tend to be hypoxic, it elevates oysters off the bottom and prevents sediment burial. So the amount of shell going in and the rate of shell loss below, those really are important for maintaining all of these functions. All right, so what exactly would cause a problem with a shell budget? Well, it depends on if there's a balance between the input and the output. So the initial net loss of shell, that can actually start a runaway cascade. What happens is once a little shell is lost, it causes a degradation of function, and that affects recruitment. It affects sediment burial, which causes more shell loss, which causes more degraded function, which causes more shell loss. So it just keeps going and running out of control. So there's a couple of factors that can cause these systems initially to move into this net shell loss state and trap them in this collapse state. Overharvest, culture removal, and recruitment failure, all of those can be initial triggers. And I'm going to focus the rest of my talk mostly on Tampa Bay. That's because that's where I live and work. This is from the OIMP chapter on Tampa Bay and Sarasota. And it shows landings. They spike in 1960, then they collapse really sharply after, and they never really return. But this decline actually happened probably in the late 1800s. That's probably when things really took a turn. These landings data from the late 1800s, they're not perfect because there's a lot of biases that I don't have time to go into. But they do record that there were much higher landings in the late 1800s compared to what the OIMP chapter showed. And we know that just from other historical records that after the Civil War, people poured into Florida looking for work. And because there wasn't a lot of industry in Florida at the time, uh, fishing and harvesting of Florida's resources, that's really where a lot of people went to work. And over again, you can see in Tampa Bay and elsewhere, you can see a lot of these resources collapsing very, very rapidly within a decade or two. So I think this early collapse of oysteries probably happened quite early, and I think it's substantial if you also look at the historical records. The extent of these depletions was extreme. Smeltz wrote in 1898 he had been traveling through Florida 20 years earlier, and he said every one of the major bars along the West Coast was depleted. He specifically mentioned Tampa Bay. And then there's newspaper accounts from 1900s, early 1900s, where oyster fishermen from Tampa would go, once they depleted everything in Sarasota, they moved down into little Sarasota Bay. They carried everything except the water and the sandy bottom. So they were taking shell. And this is shell that would otherwise end up in the shell budget. They were taking everything. In addition to overharvest and removal of cults, there was reef mining in Tampa. It started in the early 1900s and went through the 1970s. In a lot of places, they were mining prehistoric reefs that were from the middle and late Holocene. But in some cases, it was documented that they were actually dredging live reefs. They were using these for construction materials, but also for road base. And we know that they were harvesting live reefs because there's some accounts that Damon Morris has mentioned in some of his talks about how the roads stunk for weeks afterwards because all the live oysters that were dumped on the roads. There's also some really fascinating survey maps, engineering maps from the late 1800s, also that Damon has brought to our attention. But what they showed is they went through and they mapped all the reefs that were in the Manatee River, and they are marked here in blue. But these were removed they were dredged for navigation. And again, this all happens in the late 1800s. So this is removal of large amounts of dead shell, obviously completely eliminating reefs in some cases, but in other cases, obviously affecting the shell budgets. So my research goes into that a little bit, but I'm also interested in historical declines in shell size and shell thickness because those also affect the net shell mass that's added to a reef and is really important for the shell budget. Shell height is a function of longevity. So the longer lived an oyster is, the larger it gets and the more shell mass it can contribute to the reef framework when it dies. And shell thickness is also important. The thicker oyster contributes more shell mass, and that's affected by pH, alkalinity, and other factors. This graph was I think, a recent graph from Roger Mann's work. But again, it's from the Atlantic coast. We have the same relationship in Florida, but as shell height increases, shell mass increases exponentially. We are finding the same relationship here in oysters too. I just don't have the raw data ready just yet. But the significance of this exponential increase is that if there is even a relatively small decrease in longevity, that should result in an exponential decrease in shell production, shell mass per individual. And if you look at the shell height there, around 90 millimeters, 100 millimeters, that's close to the maximum height that oysters get today, which means that modern oysters don't ever really reach the exponential mass increase phase with shell growth. They just have the linear phase. So What this means is that as size has decreased, there's been a huge shortage of shell mass being added to reefs. On the right, there's 2 to 3 inch oysters. On the left, there's a 6 inch max oyster. This is from Old Tampa Bay. And these are the largest, the 6 inch, that's about the largest that oysters get in Tampa Bay today, to my knowledge. But there are archaeological oysters that we've found in collections that are well over 10 inches, 11 inches. And I know that really large, close to foot long oysters, they've been documented in historical accounts all along the Atlantic coast for quite some time. This is the largest oyster that I think has ever been encountered in Florida. So this is the magnitude of size decline that's happened here locally. We just published a paper. There's a PhD student, Jamie Rogers, was lead author on this. But this paper looked at archaeological records of size spanning the last 2,000 years and all throughout Tampa Bay. So from the upper part to lower Tampa Bay. And one of the fascinating things that he found was that there was actually early size decline. So there were altered shell budgets starting around 2,000 years ago. There may have been some recovery, but there's definitely been a decline even more recently, probably all of it probably due to overharvest. I do want to add that it's not that we're just adding less shell to the reef. This also can cause an alkalinity crisis for the reef. And what I'm referring to is that when dead shells are in the reef framework, as they dissolve, they actually contribute to an increase in alkalinity above where recently recruited oysters are growing. So when there is the direct removal of shell from dredging or over harvest of culch, or if there's size decline, both of those decrease the amount of shell mass that's in the reef framework available for dissolution, and that can contribute to alkalinity. So what I'm basically getting at is that once we start going into this net shell decline because of size decrease or thickness decrease, over time, that's going to set off an alkalinity time bomb. Initially, there's still a reservoir of massive dead shells, but give it a few decades, and eventually there's only smaller, thin shells in the reef framework. Alkalinity drops rather rapidly, and shells that are now at the surface are having a hard time calcifying, and that ends up in another feedback loop that contributes to net shell loss. There's also been some work again out of Holland Mann's lab where the modern shell budget, shell thickness is affected by salinity, specifically low salinity. Freshwater tends to have lower pH, lower alkalinity. And this is there was an experiment done this is Pacific oysters, but under acidified conditions, you can see what happens to very young spat. And this is from Markart et al. This is from 2024. And it shows that the low salinity is on the left and the higher salinity is on the right. And what this shows is that shell mass added per shell length decreases at lower salinity. So there's less shell mass added per individual to the reef framework at lower salinities. This happens in Florida as well. I'll give the example from Manatee River because it's a pretty good example. Here we can see that the Manatee River has relatively low pH. I think the average, the average pH there is around 7.6, which is almost too low for normal calcification. So that's a pretty big problem. But this is exactly where modern oysters are located within the river today. All the little white dots that you can see there, they're circled in orange. Those are where the modern reef locations are currently. So they're from Bradenton and Palmetto upstream. Downstream towards the open bay, we don't have these. I think why these the distribution is the way this is because during a drought, there's mortality in the lower parts of the river where there's higher salinity that forces the reefs up stream, and then they get trapped there. But what's really interesting is that this is not where oyster reefs used to live. So I've been working with archaeologists from USF, and the map on the right shows each one of those little dots is the location of a shell midden or a shell mound. And if you look down by the Manatee River, there's almost no midden and mound sites that are up the river. They're all near the mouth, the high salinity part. And there's actually, as you go from upper Tampa Bay to lower Tampa Bay, along that increasing salinity gradient, that's also where you get the most middens and mounds. So in the past, oyster reefs were located more away from freshwater sources and more in the high salinity parts of Tampa Bay. We've confirmed this. We've gone through archaeological midden shells and we've done extensive geochemistry. We haven't published this yet, but these two graphs just show that the oxygen and carbon isotope geochemistry of shells varies as a function of salinity. So we've actually confirmed high salinities from these oyster midden and mounds. They weren't collected from other places. There's also the historical maps. I think I showed previously the engineering maps for the Manatee River. In the blue, this is where the historical reefs existed up until the time they were dredged in the late 1800s. So we can see that the modern distribution of reefs is really unusual. And because the oysters have moved upstream, now they're trapped in areas where there's low pH, low total alkalinity, low calcium ion availability. In the inset map below, what I've done is I've highlighted the locations of shell middens and shell mounds in purple, and the presence of the modern oysters. That's the little gray dots to the right. And you can see that their distributions are quite different. So based on the geochemistry of the shells, prehistoric people were harvesting oysters in the higher salinity parts of the bay. They weren't going upstream and transporting them downstream. So the places where oysters are growing today is highly unusual. It's a novel habitat. I also highlighted a seagrass layer here so you can see that. I think that overlapping distributions is probably important because seagrass photosynthesis also has an impact on pH and alkalinity. I know today in the oyster suitability index for Tampa Bay, wherever there's seagrass, that's not a place where you should put oysters. But in the past, those two habitats were probably intermingled. I think that's kind of what this distribution is telling us. But today, oysters throughout the bay, but I think this example of Manatee River really does show it. The oysters today are in novel habitat and arguably suboptimal for calcification and shell budgets. So wrapping up, I think I talked about three of the goals for FORS for status and trends assessment. I've talked about how shell budgets have changed. For critical tipping points for barriers for oyster management. Again, it's shell budgets. There's probably a critical tipping point that oyster reefs have passed. It's been documented elsewhere. I think this also applies for Florida and Tampa Bay specifically. And then for FORS Goal 2, consensus on metrics and modeling parameters, I think shell mass and shell budgets, we need to pay more attention to that. And I think that could have good lessons for restoration. And I have one more slide. And this is a quote from Jeremy Jackson's paper, 1997, called Reefs Since Columbus. And it's about coral reefs, but I think it applies here. He's talking about the shifting baseline in that paper. And he said it's the shifting baseline management. It's a consequence of the growing eco-management culture that accepts the status quo, fiddles with it under the mantle of experimental design. We're kind of doing that now by just messing around with oyster substrates, restoration substrates. And we're doing that without any clear frame of reference to what it is that we're trying to manage or conserve. And it's kind of a harsh statement, but I think it does apply here because a lot of times we are doing these restoration projects without understanding the history of these ecosystems and how they functioned in the past. Some of the reference points that I talked about today were oyster size and life history, which are quite different, shell budgets and alkalinity, which are also different, and obviously salinity and proximity to seagrass, where oysters are now is today is a novel habitat. So thank you.
Thank you, Greg. That was fantastic. And if there's any questions, I don't see any right now in the chat, but feel free to unmute yourself if you have a question for Greg. And I do have one question that I wrote in the chat just to kind of kick it off. So I recall some work done in the Pacific Northwest looking at differences in alkalinity in areas and how that have impacted shellfish growth um, in seagrass beds and outside of seagrass beds. And so I'm wondering if that's something that we should be looking at more closely in terms of siting downstream restoration projects. Obviously, we don't want to impact the bottom as it relates to seagrass, but maybe that's something to kind of help with the alkalinity issue.
Yeah, I can comment on that. I know that with let's just give an example of coral reefs and mangroves. Depending on the proximity of those two kinds of habitats, mangroves can actually contribute in a healthy way to the alkalinity of waters that corals are growing in. And so there's been a lot of studies there about the synergy, but the interactions between those two ecosystems and how they can be beneficial. I don't know of too much research. I haven't looked that hard just yet, but I don't know of too much research on seagrass oyster interactions the same way. But given the archaeological evidence for where these oysters used to live, I think we have to consider it.
Mm-hmm. Yeah, I think some of the work in the Pacific Northwest was looking at using aquaculture as sort of like that experimental framework to say, okay, how well are oysters growing either sort of within those seagrass areas or adjacent to versus just barren mudflat areas. And I haven't followed up exactly on the papers, but I just recall that from a conference. So we have we're starting to get some questions. Caitlin was asking if a PDF of these slides could be made available. Is that
Sure?
Okay? Great. So I guess we'll send those out through the listserv. Would that be appropriate, Katie?
Yes, we can certainly
Yeah, I'm
do
fine with
that.
that.
Okay, great.
Greg.
Thank you, Greg.
Thank you.
We've got a question here from Morgan. Do you collaborate with any companies or organizations sharing your research to inform their conservation or restoration efforts?
No, so I'm based at a research university, so I have not done it. I haven't reached out in that way, but uh, I'm happy to talk to anybody who has got ideas about, how to apply some of these lessons.
Great. Stephen's got his hand raised. Go ahead, Stephen.
Yeah, hi, Greg. Thanks. That's a really interesting presentation. I was curious about your thoughts on how, like, I totally understand the sort of critique of working on the current ecosystems, um, filling around the edges or whatever the Jeremy Jackson was saying. But how would you, like, do you have thoughts on how you would actually get a system like this out of this sort of uh, like post tipping point state? I mean, it strikes me that you're talking about um, the reefs sort of being pushed into fresh waters by conditions, like drought conditions and things like that. But then um, it seems like the loss of high salinity habitat um, sort of leaves the existing populations vulnerable when then you have the opposite condition and there's nowhere for them to resettle in those, you know, the former locations. And so I'm kind of wondering if you have evidence that maybe like populations used to almost like bounce around between reefs that were persistent over long periods of time, or if like how do you get that dynamic back now that the habitat's gone, right?
Yeah, so great question. Yeah, so I didn't have time to go into it in the talk, but I'm happy to elaborate. So I think Bill Pine has done some experiments, some restoration experiments around Sewanee, where dumped giant dolomite boulders off the coast, and they engineered a reef chain. That's really important. I think that's kind of what happened in Tampa Bay, at least. There were high salinity reefs. I'm pretty sure of that, just based on the archaeological and geochemical evidence, and also the survey maps from the late 1800s. Those probably performed a similar function of impounding fresh water. Once those outer high salinity reefs were gone, rivers, the estuarine condition, the conditions behind those reefs dramatically changed. There's a faster freshwater flow times out into the bay, the retention times decrease. And I think that's really probably the event, the collapse event that forces oysters upstream. It just takes one drought to basically push them upstream after that. To get things back, your question is how do you reverse things? I think you would have to consider uh, experiments like what Bill Pine was doing, where you're basically re-engineering some of these functions of the reef before the oysters can do that for themselves.
Thank you. One follow-up. Do you see these reefs? I mean, some of them in the maps in particular are really quite large. Um, like, are these features that originated, kind of like an Apalachicola? Do you think they originated in the essentially Holocene? Like
Yeah.
they're a consequence of like very long-term geomorphologic processes that are difficult to like replicate?
So that's a great question. So there's a geologist named Twitchell who did a really interesting paper on the Apalachicola reefs and showed that they were, 2 to 4,000 years. Their reefs are basically really long-lived features up there. I don't know that the rest of Florida necessarily works that way. Tampa Bay doesn't have kind of a similar setup. It's more of a sand dominated, really, it's more of a dynamic kind of a system. And when we have done coring, we haven't really found old reefs.
Oh,
So
okay.
we have a project that's active now. We're working with the USGS. The USGS is leading it, um, and they're looking for evidence of older reefs. But it's possible that Tampa reefs uh, are much more dynamic. They set up and die a little bit more frequently. And what are the implications of that? I don't know yet, but
Okay. Yeah, it'd be interesting to see like in some of the reefs that are still there now, um, like the ages of the material from buried deeply within them to see it like are they uh new, in quotes, new, um, like or are they, do they go a long way back and what the implications of that might be for the reefs, the former high salinity reefs that are now apparently just like excavated out of existence. But
yeah.
thanks. Yeah, really, really cool talk. Thanks.
Thank you, Steve.
Thank you, Steve. Yeah, thank you, Stephen. Um, Greg, we've seen a number of us have seen Bill Pine's presentations, and yeah, it's really interesting work. I'm wondering, have they also, with that level of, restoration, and they've looked at the oysters, has there also been, has anybody also been monitoring the changes in oceanographic conditions that come as a result of that?
Oh yeah, they
Like
did.
changes in residence time. That's part. I probably just haven't seen that. Yeah.
Yeah, there's been some reports that they published. Fredericks, I think, might have been the author on one of the reports there. But yeah, that was the whole point, was to see if they could change the residence time of freshwater and how that would affect shell growth and survivorship.
Cool. Yeah. Thank you. Awesome. Any other questions from the audience? Either enter in the chat or go ahead and unmute yourself. If there's anybody. All right. Well, Greg, thank you so much. That was fantastic, and we look forward to hearing more. And we will. I'm recording this right now, so we will post this on our YouTube channel. And again, you can get to the link for that YouTube channel in the link that Katie posted in the chat to the FORS website. But thanks everybody, appreciate it, and we'll see you in September 17th for our next webinar. All right. Thank you.